In our previous lessons, we discussed two types of oscillation. We discussed the free oscillation. We discussed the damped oscillation. So in both cases, there was no external force which is applied. And we saw that most of the times there will be an external force applied. For most of the systems that we model, there will be an external force. Like in the electrical circuits, it's not likely to have a circuit where there's no source. So the same for mechanical circuits, there will always be some force applied. So that is what brings us to the forced oscillation. So we'll discuss the same circuit that we discussed in the damped oscillation. The only exception now is that there is a force which is applied. So if you refer to our previous lesson, then we had our circuit. We had the spring. Then we had the damper. We had the damper. And then we had our mass. But now we want to apply a force. So the same equation would still apply, except that now we are applying a force given by F equal to F E J omega T. So in the steady state, the oscillator would oscillate at the same frequency as the applied force, and will have X being given by A, E, J, omega T. If we substitute this in our previous equation for the motion, then we'll have m d squared x dt squared plus rm dx by dt plus sx gives us f e j omega t. And we can apply, we can bring x here the same way we are done in our previous lessons. And if we differentiate twice, then what we have, I will have m, then minus a omega squared e j omega t. Because if you differentiate we are seeing that if you differentiate x twice, that is dx by dt, gives you, this one comes down, j omega a e j omega t, then d squared x by dt squared gives you j squared omega squared a e j omega t, which is equal to minus omega squared a e j omega t. So we can always substitute for this in this place, so that we have we have this expression. Actually, I can rewrite it down here, so that we have m minus omega squared a e j omega t plus the Rm, then I have J omega A E J omega t plus S A E J omega t equal to F E J omega t. If we cancel out the J omega t here with this one, because we on the left-hand side, we can factor this out. Then it cancels with what we have in the right hand. Then we'll have the negative of, I will have, let me see, I will have minus A of M omega squared plus R M J A omega plus S A plus plus S A equal to F. If we make A the subject of the formula, then I will have A equal to F over minus M omega squared plus J R M omega plus S. Remember what A was in the expected solution. A is this maximum amplitude here. So we are saying that A is equal to this expression, which I can actually write. I can write A in this manner. A is equal to, if I factorize J omega and bring J omega out, and bring J omega out, so that I have 1 over J omega into F over remember this one has come out. Yeah. So we have Rm. Then plus for this, I will have, because J omega have come out and J omega was not there, I'll have S over J omega. That when this J omega comes inside here, it multiplies. It multiplies I think the best is write it here 1 over J omega. So it multiply this and we'll win with S. Then I will also have minus M for this, M omega actually M omega J. So that when this one comes, it multiplies J squared. J, this and this gives us omega squared. Actually, it will have a plus here. So that when it comes down here, I can have 1 over J omega into F over Rm plus J into M omega minus S over omega. So X A is equal to this. This means that if I have to substitute it, since we had X equal to A, E, J, omega T, then I can now have X is equal to F, E, J, omega T, because now we are substituting for A over J omega into Rm plus J into omega M minus S over omega. So this is the expression for the displacement. So if we look at the numerator, this part, it resembles what we know. It's really about the resistances. It resembles what we know. So because it looks like we can actually denote it by Zm, refers to mechanical impedance. So that I have Zm equal to Rm plus J into omega M minus S over omega. So where we can say where Zm is mechanical impedance. Where Zm is mechanical impedance. So if we look at this expression, then now we can equate the mechanical resistance to this. And X of M we can equate to omega M minus S over omega. In fact, following this notation, I can have X being given by F E J omega T over J omega is this Zm. And if this is the displacement, then we know that the moment we have displacement, then the velocity u would be given by u equal to dx by dt. So dx by dt, d by d, t of this j omega t over j omega z of m gives us, you can see this part will come down so that I have j omega into f e j omega t over j omega zm. That j omega comes with j omega. So we'll get u equal to f e j omega t over zm is equal to f over zm. In fact, if you look at this equation, then we are saying velocity is equal to force over impedance. So we should start considering the analogies, because we are seeing that U equal to F over Zm. And we also know from electrical circuits that current equal to voltage over impedance. So we can straight away conclude at this point that the velocity in mechanical circuits is the analog of current. If you look at the way we obtain them, because U equal to F over Zm, I equal to V over Z, and velocity, sorry, and force actually corresponds to voltage. Voltage corresponds to force. So this is something that we can conclude at this stage. So as we move on, they're analyzing the rest of the variables. Then we can also see that from this expression of Zm equal to F over U, actually you can put the units if you want to get the unit of Z of M, because F is in newtons. So I can have F in newtons, velocity in meters per second, so that I get Zm in newtons seconds per meter. And we know that if we have impedance Z in the electrical circuits, then the magnitude will be given by R squared plus Xm squared, the root of this. We can actually apply this. We can apply this to Zm, Rm, Xm. And we can still be able to draw the impedance triangle. Remember the impedance triangle that you have. I have the three sides. You have the three sides. Rm, XOM, Zm, then you have this angle theta. So I can get the other parameters like the angle theta, tan theta, equal to opposite or adjacent, or x of m over r of m. And theta is equal to this tan inverse x m over rm. And remember the power factor, we can also get the power factor here, which is the cosine of this angle. We can also see that because of course xm, if we put the values of xm here, then we have theta equal to the tan minus omega m s over omega over rm. Then we'll have, this is what we'll get. We are still able to get to do many things like if I can write, if the angle is theta here, I can write Zm as being equal to Zm at some angle, E, J, theta. Remember, theta is now the angle between the xm and the rn, and x, if we now put in the value of x, we'll have 1 over j omega f e j omega t over zm e j theta. So that I can have, of course, if we expand this, will be 1 over j omega into f, the cos of omega t f into cos omega t minus theta plus j sin omega t plus theta over z of m. So that the real part of x, is given by f over z of m omega sin omega t minus theta sin omega t minus theta, and the real part of u will be given by f over z of m cos omega t minus theta. So these values are very important because we want to calculate them to get the power in the circuit. Like in this electrical circuit, the moment you have the voltage, you have the current, you can get the power. So we can apply the same concept to the mechanical circuits, acoustic circuits, and the rest. So in a circuit like this, then the power, you are to get the power, then the power will be given by, let's denote the power by pi I. So pi I, which I refer to instantaneous, will be given by like the voltage times current. If it's in an electrical circuit, we'll have voltage times current. Now in our case, what corresponds to the voltage is the force. Then we multiply by the current, and what corresponds to the current is the u, or the velocity. So that now when we evaluate this, we get f cos omega t f over zm cos omega t minus theta. And if we simplify this one, then we get f squared over zm cos omega t into cos omega t minus theta. And the average power, actually the average power is more important. So you can talk of the average power. The average power will be given by pi equal to 1 over t, the integral 0 to t, pi I dt. That is getting the power in one cycle, which we already have there. And if we do that integration, let's integrate from 0 to t f squared over zm cos omega t cos omega t minus theta dt, then what we get will be equal to f squared over 2zm cos theta. So we are also interested in when is this power, when would this power be maximum? When would the power be maximum? The power in this circuit, when would it be maximum? Definitely it would be maximum when Zm is minimum. It will be maximum when Zm is minimum. Because you can see actually we can replace, when you want to get when the power is maximum, we can replace the cos theta there. Because you can see if I have my theta, I have down here I have Rm, I have Xm here, Zm, then cos theta equal to adjacent over hypotenuse, that would be Rm over Zm. So I can replace this one here. So that I have pi equal to f squared over 2Zm squared Rm. Because if I replace this, there will be a Zm coming down here and Rm going up there. So, so that I am able to have this power in terms of only one unknown. This would, so that I don't think about minimizing theta and also minimizing z of m. So we'll have 2 z of m. So that the only question that we can now ask ourselves is when the Zm would be minimum. And we know the expression of Zm. We know that Zm equal to m omega minus SW plus R of m. And this one becomes minimum if this component is equal to 0. And that is what we'll do. We'll equate this component to 0 so that we have m omega minus s over omega squared equal to 0, so that I have m omega minus s omega equal to 0. And if you work this one out, then you'd have omega squared equal to s over m, or omega is equal to s over m, the root of this. And you can remember this expression. It is what we had equated to the fundamental frequency of oscillation. So we had equated this to omega naught. So what this means is that you have a system, you are applying some force, external force, but we are interested in when would the force be maximum. It will be maximum if this force has a frequency which is equal to the natural frequency of oscillation of the system. And that's what we call the resonant frequency. That the system we are considering is already having some natural frequency of oscillation, natural in the sense that if you don't apply any force, then what is the frequency of oscillation? So the conclusion we have here is that for the maximum power to occur, then the applied frequency, the force should be applied at a frequency equal to the natural frequency of oscillation of the system. So that is a very important part of the conclusion that we may need to make. In fact, we can look at it from another perspective. I can have some drawing here. Let's say I have a graph of power against frequency. So we say the power would be maximum when the frequency is equal to the natural frequency of oscillation of the system. And of course, we know that power we are talking about, power is equal to F squared R of M over 2Rm squared. The reason why we are saying this is because we had actually found out that the power is given by, if you look at this, F squared Rm over 2 Zm squared. We had F squared Rm over 2 Zm squared. But we have found that at maximum power, Zm equal to Rm. So at maximum power, we can substitute the Rm here so that we have this expression where you have Rm squared. You can see the Rm and the Rm, one of them would cancel so that we have pi equal to F squared over 2Rm. So what we want to define here is something that's called the Q factor. The Q factor of the circuit, or the quality factor, or the parameter that describes the parameter that describes the power, the particular power that we get at the resonant frequency. So if you look at the graph that we have drawn here, we can actually define what we call the Q factor by, let's say, this point where we have half the power. Let's call this lower frequency WL, and this upper one W upper, or W lower, W upper. And if we do that, then the what you call the quality factor, we define it by what W naught over WL minus W upper. Actually, W up mana WL, not WL mana W up. W upper mana WL. Okay. So from the equation of the average power, you can see we have already obtained we have from the equation of the average power, the equation of the average power, you have seen that average power is equal to F squared Rm over 2 into Zm squared. If Zm equal to 2Rm squared, if F is, let's assume Zm equal to 2Rm squared, so that we substitute 2Rm squared there. Then we'll have pi is equal to F squared Rm over 2 into 2Rm squared, which would be equal to a half here into F squared over 2Rm. Into F squared into 2Rm, which is the half the average power. Half the average power. Half the average power. Because you can see, let's just go over this just a little. I've taken the half outside, so we remain with F squared. Then 1 of the Rm cancels with the 1 of the Rm, so we remain with F squared over 2Rm. And this is what we are seeing to be maximum power, which is this. Yeah, we have just chosen, let's say, through trial and error. But what we can see is that this power will actually corresponds to this point. This point, the power at this point. So this is the half maximum pi at this point. But now we find out that if we substitute Zm squared equal to 2Rm squared, then the power we get is at this point. So we are able to get this, we can get these frequencies because if now we say Rm squared plus Xm squared, which is equal to Zm, is now equal to 2Rm squared. Then now you can see, let's use this and this. You can see from there that Xm squared is equal to Rm squared, or X is equal to plus or minus Rm. That is to say, omega m minus S over omega is equal to plus or minus Rm. And this means now the upper frequency omega u minus S over omega will correspond to the positive one. And the lower frequency omega low minus SW will correspond to the negative one. And therefore we are able to solve for omega u minus omega L equal to Rm over m. Therefore, we can write the new expression of the Q factor. It is now omega over omega u minus omega L is equal to omega naught over Rm over m. Is actually equal to omega naught over 2 beta. Omega naught over 2 beta, which is also the same as 1 over 2 omega naught tau. Remember how we are defined tau as 1 over beta. So we are able to relate the Q factor with the damping factor with the relaxation time. So Q is equal to 1 over 2 omega naught tau or omega naught over 2 beta. So this ends this slide. In our next slide will be very short. We'll discuss the equivalent electrical circuits with the equivalent electrical and mechanical circuits. Then we'll have a solution to some few tutorials before we discuss the acoustic systems and relate them to the mechanical systems.